Most AI we use today is kind of built like a skyscraper. It's rigid, it's meticulously designed from the top down, and honestly, it's pretty fragile if you mess with a blueprint. But what if we could grow an AI? Like a crystal? Or what if it could learn like a flock of birds? So today, we're going to dive into this pretty radical new idea based on some amazing research by Kara Rossen that imagines an AI that literally organizes itself from the ground up.
So here's how we're going to break it all down. First, we'll look at the problem this whole idea is trying to solve. Then, we'll get into the wild concept of a particle swarm AI. After that, we'll see how these little particles actually talk to each other using vibrations. Then, we'll cover the single, simple rule that makes the whole thing work. And finally, we'll ask the big question: what could this all mean for the future of intelligence?
All right, so first things first, why do we even need a totally new approach? Well, the problem is baked right into the architecture of most of the AI we use every day. Now, this slide really gets to the heart of it. On one hand, you've got conventional AI. Its connections are fixed in place, its structure is painstakingly designed by a human, and that makes it, well, brittle. If it sees something it wasn't specifically trained for, it can just completely fall apart. But then, look at nature. Think about your own brain or an ant colony. They're the total opposite, right? They're dynamic, they're resilient, and they self-organize from these super simple local interactions. So the research asks a really cool question. Can we build an AI that learns more like nature does? And that question leads us directly to the core idea of the paper, a completely different kind of a learning machine. This right here is the central idea, and it's a big one. I mean, forget everything you know about layers of neurons and fixed wiring. Instead, just picture a cloud of individual particles floating in space. They aren't programmed with complex instructions, they just exist. And somehow, through their interactions, intelligence emerges. Now, to understand how that's even possible, we need to borrow a key concept from neuroscience. And that concept is called predictive coding. The easiest way to think about it is that your brain is basically a prediction machine. It's constantly guessing what's going to happen next based on its own internal model of the world. And when reality doesn't quite match its prediction, that creates what's called a prediction error, or what neuroscientists sometimes call surprise. Your brain hates being surprised, so it updates its internal model to reduce that surprise next time. And that, in a nutshell, is learning. This new AI model is built on that exact same principle. So, what exactly is a particle in this system? Well, it's actually defined by four really simple properties. First, its position, just where it is in 3D space. Second, its activation state, which is basically the little piece of information it's currently holding or predicting. Third is its vibrational phase. Think of it like an internal metronome, its own little rhythm. And finally, its intrinsic spin, which helps it figure out how to talk to its neighbors. That's it. These four simple things are the Lego bricks for building an emergence intelligence. Okay, so we have these particles with their simple properties, but how do they actually form a network? How do they communicate? It turns out they have this surprisingly elegant language. And it all boils down to two fundamental ways they interact. First, you've got simple physical forces, almost like tiny magnets, pulling them together or pushing them apart. And second, and this is the really cool part, they communicate through their vibrations. Let's take a look at how these two things work together. This graph just shows it perfectly. See those dotted lines? That's the pull of attraction and the push of repulsion. But when you combine them, you get that solid line, the total energy. And notice how it dips way down into that little valley? That's the sweet spot. That's the low energy, stable distance the particles are all naturally trying to find. It's what gives the whole swarm its basic shape. Now for that second language vibration. On the right, you can see what the paper calls vibrational coupling. The best way to think of it is like a bunch of tuning forks. When two particles start vibrating in sync with each other, their connection gets stronger. Information flows more easily between them. And this is how the network dynamically builds and rebuilds pathways for information. It's not about fixed wires, it's all about synchronized rhythms. Okay, so we've got particles that can arrange themselves in space and communicate through vibration, but what's the engine? What makes them actually learn? Well, it all comes down to one beautiful, overarching rule. That rule is the free energy principle. Now, don't let the name scare you. It's really just the mathematical version of that whole minimize surprise idea we talked about earlier. The entire system, every single particle changing its position, its activation, its vibration, is all driven by this one single goal. Arrange yourself in a way that makes the world around you as predictable as possible. Think of it like this energy landscape here. A state of high surprise, where you don't know what's going on, is like being at the very top of a hill. It's a high-energy, unstable state.
The system naturally just wants to roll downhill to find a valley. And that valley, the global energy minimum, that's the configuration where the particle's predictions best match reality. It's the state of least surprise. And here's the most profound part of all of this. There is no master controller. There's no top-down blueprint telling everything what to do. Each particle is only following these simple local rules. Try to stay a good distance from your neighbors, try to sync up your vibrations, and above all, adjust yourself to minimize surprise. That's it. And from that simple foundation, something incredible emerges. This is what you get. The process is called morphogenesis, which is really just a fancy way of saying the beginning of shape. Just by following that one simple drive to minimize free energy, this random swarm of particles spontaneously organizes itself into complex, stable, and information-rich structures. It physically learns to embody a model of its world. It builds itself.
So what does this all mean? I mean, if intelligence can emerge from such simple rules, what does that actually imply for the future of AI? This is way more than just a cool science experiment. The implications are huge. For starters, this could point toward AI that is truly adaptive, systems that can physically restructure themselves to learn new things. It suggests AI that's way more robust. You know, if some particles get damaged, the swarm could just reorganize around them. It's also way more biologically plausible, bringing us a little closer to how our own brains might work. And maybe most importantly, it challenges the entire old-school idea of fixed, hand-designed AI architecture.
And that all leaves us with this one final, kind of mind-bending question. We tend to think of intelligence as abstract, right? As software running on hardware. But this research suggests that true, adaptive intelligence might not be something we just program. It might be something we have to grow. A physical process of self-organization emerging from the simple dance of particles just trying to make a little more sense of their world.